Have you ever eaten food or maybe taken medicine? Have you ever wondered how these molecules get metabolized in a series of reactions to keep us healthy? Great! Because the novel Python package Tellurium allows you to analyze and simulate models of biochemical and cellular systems with ease. Tellurium was designed and created by our friend Professor Herbert Sara and
Hello
his
there.
amazing team of researchers. They designed Tellurium because of how many challenges they saw in modeling biochemical systems while ensuring reproducibility for other researchers. This is an example of a system we might be interested in modeling, the reaction network of glycolysis.
Holy
Many of you
cow.
might be familiar with how many different enzymes, substrates, and intermediate species there are in this network. Tellurium allows us to analyze these networks with ease and explore the effects of various changes on the system. For example, we can analyze the effects of varying initial conditions or look deeply at the reaction rates at any step along the way. But rather than jumping into such a complex network, let's start with a simple example. Here's a common system that describes an enzymatic reaction. The enzyme and the substrate will bind to form an enzyme substrate complex in a reversible manner. Once they bind, the product will be formed and the enzyme returns to its free state, ready to bind another substrate. The reaction constants K1, K2, and K3 specify the rates at which each reaction occurs. Without tellurium, we'd have to write out all the differential equations for the change in each species, use a system solver, and then import our favorite plotting package to look at the results. All of this for such a simple model? Nobody has time for that. But here's where the magic happens. We can import Tellurium and set up our model with just a few lines of code. We'll set the initial conditions and then easily simulate and plot the model. And when we run this code, voila! For those of you who love chemistry, we can see that after the immediate spike in enzyme substrate binding shown in green, as the substrate concentration decreases, the enzyme gets less saturated, leading to more free enzyme shown in blue, and the product in red accumulates over time. Now, this is quite a simple model, and for complicated systems, it's even more dramatic what kind of difference tellurium makes. This is also just the surface of what tellurium is capable of. There's plenty more to explore and understand in the world of computational systems biology. And now that you've seen an example of what Tellurium can do, let's give it a try on our own. Thank you very much, Shivesh. Hello, everyone. My name's Shivesh, and I'm here to take you through the basics of Tellurium. So we're going to start here in Visual Studio Code, and I'm going to go through a simple model with Tellurium. So the first thing, if you're getting started, is that you have to have Tellurium package installed. If you don't have that done, what you're going to have to do is go and make a new terminal here. And when that pops up, hopefully you're in PowerShell and you can use the command pip install Tellurium. Now, I already have it installed, but I'll just run it to show you that it works. And likely what it'll do for me is tell me I've already got everything installed. Perfect. So I'm going to go ahead and close. Okay, and now that we have Tellurium installed, we're going to go ahead and import it. We normally do that as TE to make our code a bit simpler. And we're going to set up a model. So in this example, we are going to go through a simple reversible reaction. And when we set up a model in Tellurium, we're going to wrap it inside these triple quotes. You can use single or double quotes. It does not matter. And I'm going to set up this reaction between two species. We're going to write it simply as the two reactions with a little arrow. And this means species 1 creates 2 and 2 creates 1. Now we're going to need to specify at what rate do these reactions occur. And so we have some rate constants K1 and K2. But we're going to need to make sure that we're multiplying those by the concentrations of our reactants. And from there, We're almost done with our model. We just have to specify some initial conditions and specify what those parameters are. So I'm going to go ahead here and say S1 starts at 10 and K1 is 5. S2 starts at 0 and K2 is 4. And that's it for our model. Now, this model is written in an antimony language, so we're going to call this function called te.load_a for antimony. And you see here it says load model from the antimony string. So we're just going to go ahead and put in our model there. And now it knows that, okay, it's created this object. We're calling it R because it specifies a roadrunner type. And we're going to go ahead and simulate this model with the parameters that we've given. Now we store that in an object called data, and that's going to give all the data as this model occurs, starting from the initial conditions and then reacting and going until it reaches steady state. Okay, we're done. All we have to do here is give it a little plot. And when we run this code, and here we go. So now we have our graph, and this is going to show our model simulated over time. We'll see that S1 in blue starts at 10, and it comes all the way down here to our steady state value. And S2 starts at 0 and reacts and comes up above S1. So you might realize that the steady state values are proportional to K1 and K2. Now, since K1 is 5 and K2 is 4, that means S2 is created faster than S1, and that's why its steady state value is higher. We're going to go ahead and look a little bit more into reaction kinetics to understand the steady state values, and then finally look at a complicated model and wrap up. Thanks. So this is the same reversible reaction we just looked at. And we can understand the change in each species concentration over time by looking at the rate it's produced minus the rate that it's consumed. So here, if we wanted to look at the steady state, we can set those rates of change equal to 0 because there should be no change in concentration at the steady state. So we can plug in the variables that we know and set them equal to 0. And then finally, we have one more equation. Based on our initial conditions, we know that the total concentration in the system, S1 plus S2, must equal 10. So when we add in that equation and solve this system, we can find that the steady state value of S1 is 4.4 and S2 is 5.5. And this is directly in line with what we saw in the graph produced by Tellurium, showing that we can solve our systems analytically and graphically and get the same result. So we're going to look at one final sequential model where we have the initial species X0 that creates S1, which creates S2. And these reactions are governed by rates V1, V2, and V3. We can assume that those rates factor in any constants like K1, etc. So again, we wrote out our differential equations for each species change over time based on the rate of consumption and production. So one really helpful way to understand all of these different rates of change is with the stoichiometry matrix N, which will encode all of the differential equations. So here I've written down the previous differential equations that we defined, and now we can see that N represents each row as one of the species and each column as one of the different rates of reaction. So if we were to apply that to this equation, we can see that the first row, S1, will have 1 times V1 minus 1 times V2 and 0 because V3 doesn't factor into that equation. And the second row, S2, is 0 times V1 plus 1 times V2 minus 1 times V3. So if we write it out fully, now we can see that all of this information is encoded on the right side of the equation here. And if we were to do matrix multiplication, we'll get the rate of change for each species in terms of the different rates of reaction. And this way we can represent them all very concisely. So thanks for coming to part 1, and in part 2, we're going to understand all of this in Tellurium with a complicated model, and then go through a summary to understand what we've learned. All right, thanks. See you then.